In this video, we'll be describing something called electric potential, which is more commonly known as voltage. Now, electric potential, or voltage, goes by the symbol V, capital V typically. The very confusing thing is that its unit, it also goes by the symbol a capital V. Now, a volt is a joule per coulomb. Now, since there's the same variable for the unit as it is for the variable, you can get expressions that are, for example, V equals 5V. And the V on the left-hand side of the equation is not the same V as on the right-hand side of the equation. The left hand is the variable, the voltage of some drop. The V on the right hand is a volt. It's like saying F equals 5 newtons, but instead of using F for force, you used N, and instead of calling it force, you called it newtonage. So you can kind of see that it's pretty easy to get confused with all this volt discussion. The other thing that's kind of confusing is that electric potential, the name, sounds a lot like electric potential energy, which is a different quantity. So be very, very careful. Electric potential is not the same thing as electric potential energy, which is one of the reasons I like to use the term voltage, just because they sound very different and it helps clarify the difference between them. Now, you're probably very familiar with the word volt because you've all probably bought and used batteries before. You have 9-volt batteries and so on, and you've seen charger adapters and know that voltage has something to do with electrical stuff. What we want to describe is exactly what does electric potential have to do with electricity. Now, we want to first talk about the type of thing that electric potential is. Electric potential is a scalar field. Scalar means that it's just a number. Unlike the electric field, it has no direction associated with it. Okay, just a single number. It can be a positive number, it can be a negative number, but it's just a number, just like energy is a number. And the fact that it's a field means there's a value at every single location. So similar when we talked about vector fields and we gave the example of arrows for wind and said, hey, if you look at a wind map, you have to draw a bunch of arrows all different locations to show you what the wind looks like across the surface of the United States. Here, if you want to show what the voltage was, you'd have to show a number at all sort of different locations. Now, this is something that you're maybe familiar with. Some other examples of scalar fields would be pressure. There is a pressure at every location in this room. There's a temperature at every location in this room, and each of these things are just one number. There's an elevation on the 2D surface of the Earth. At every location there is a single number, which is the height of the surface, aka the elevation, and then you want to show that information. You're going to do that in similar ways to showing how you show voltage, because they're similar types of quantities. Each of them are scalar fields. What we've discussed so far is the type of quantity, which tells you that it's a number and it's a number at every location in space, but it tells you nothing about the physical interpretation. What the heck is voltage? Well, voltage is both sort of a little easy idea and a tricky idea. The basic idea is fairly simple. If I place an electric charge at some location, it'll have electric potential energy. If I put twice as much electric charge at that location, it'll have twice as much electric potential energy. The voltage is just how many joules of electric potential energy would I have for that charge per coulomb of charge that I'm placing there. Now, the thing that's a little bit interesting about it gets a little bit more complicated, is that that information purely has to do with the charge that is creating the potential energy. This is going to be similar to how we found the electric force in the previous chapter, where we looked at the electric field, which broke up the problem into 2 steps. First, you'd find the electric field due to one charge at the location of the other charge. Then you would multiply by the charge, the second charge, and that would get you the total field. You broke it into 2 steps. Here it's very similar. What you're going to do is try to find electric potential energy. Again, this only happens if you have at least 2 charges. And we're going to say one of these charges creates something that will cause a potential energy. This something is called the electric potential, or voltage. Once I figure out the voltage at the location of this other charge that I'm now going to place there, that'll cause an energy for that second charge, just like the electric field caused a force. And again, I find it in a very, very similar way. All I do is take the voltage at that point and multiply it by the charge, the amount of charge that I'm placing there. Now, as an equation, this would read the electric potential energy is equal to the charge times the voltage. And to be clear, Q and V are created by two different objects. Say charge 1 creates the voltage, then it's the Q of charge 2 that you plug in. Now, since the charge that you're placing there won't change over two scenarios, let's say, for example, you move a charge from one location to another location, like moving an electron from one location to another location. The charge of that electron will not change as you move it. So if you want to know about the change in electric potential energy as you move it, all you need to do is look at the change in the electric potential at those two places. So if I want to look at a final minus initial form of the top equation and condense them together using the delta notation, I can equivalently write down that the change in electric potential energy is equal to Q times the change in voltage. Both equations are true. Sometimes the top equation is more useful, and sometimes the bottom equation is more useful. One thing I want to note about how you use that bottom equation is that there are signs associated with both the charge and voltage change. So if the voltage increases as you move from one location to the other, delta V is going to be positive. But if Q is a negative number, when you multiply them together, overall you'll get a negative number, meaning that delta PE would be negative, or in other words, that you are losing electric potential energy. So if you go from one spot to the other, and you definitely know how the voltage change, it either increases or decreases, whether or not that means that the charge gains or loses energy depends on the type of charge. Negative charge will gain potential energy when the voltage goes down, and positive charge will gain potential energy when the voltage increases. So we want to be able to find the voltage at some location. Now, the voltage depends on the charges that cause it, and it depends on where those charges are, or in other words, the distribution of the charges. We'll take a simple scenario, one scenario where all of the charge is located at one point. You just have one point charge. The electric potential created by that single point charge goes as the equation on the top. That V, the voltage, is equal to KEQ over R, where Q is the charge that is creating the electric potential, and R is the distance away from that charge. If you have two oppositely charged plates, and so you have a uniform electric field, or in general, any case you have a uniform electric field, the voltage is just going to be negative times the electric field in the x direction times x.